Good afternoon. Let's start lecture. Guys, do you have a lot of midterms not picked up yet? And if you missed the lecture, the previous lecture, come to my office to pick up the midterm. Okay. Okay. So we're gonna actually we're going away from the vector field for now, and then we're gonna do some integrals now for the next few lectures. Okay. Yeah. So this is what we're going to do today. So we're going to learn a brand new type of integral. It's called the double integral. Okay? And then after double integral, we have a triple integral. And after triple integral, and that there's no, I think there's. Yeah. Okay, so before we talk about double integral, so let's go back to a function of a single variable, and I want to emphasize a very simple concept. Okay, and then that will transition into the double integral concept. Okay. So let's consider function of a single variable, and let's say x belong to a range a to b. Okay, so here is the drawing. So this is the function, and this is the range here. As we all learned before, we said, okay, calculate the area underneath this function in here. So what do? You instead of directly jumping into the integral here. So I'll just go through the steps just to illustrate the idea here. Okay, yeah. So what you typically do is, okay, you go to let's say one single point here. This is xk location. Okay, so this x-axis, y-axis. Then at xk location, we can draw, let's say, a rectangle, right, around this x of k location. Then, if you go above to the function here, so this is basically f of xk. Good. Okay. So, and then the idea is, okay, so I can calculate the area around this x of k location, right? Okay, I calculate the area around this xk location, and that's a rectangle. So the rectangle is the height times the base length. Then we can see, okay, so the small rectangle area, so the delta s equal to the bottom length. The bottom length, so let's say we give it a small length, call it delta xk. So that's a small change around x of k xk location. So delta x of k time the length with the height, which is f of xk. Okay, so let's write the f of xk, let's say, to the right of it. That's the area of this rectangle, small rectangle. Then you can imagine you can pretty much set up the whole area underneath this, set up this whole thing with a number of rectangles here, right? Many rectangles. Okay. So the total area underneath this curve, and that basically will become, so the total area, okay, will be approximately, when you add all the rectangular area up. Okay. So when you add all of them up, and that's basically the total area approximately. Okay. So then, if you let this number of rectangles go to infinite, then the summation sign at here will become an integral sign. So basically, if you let this n go to infinite, okay, this summation sign sigma here will become integral sign. And this little delta symbol, which is a small change, instead of small change, you become an infinitesimal small change. So that will become dx. So f will become f of x. Then you have the range from a to b. So that's how you get integrals, right? So the integration essentially goes from a to b. Then you get the total area underneath the curve f of x. Okay, so that's the idea. Through approximation, how you can get this single integral of a single variable function. Okay. Now, before we move on here, right? Let's just establish another concept here. The integration, basically, when you say integrating from a to b, going from a to b at here, so what's going on here? Something wrong with the system. There's no response at here. Okay. Okay, you can take a break. Oh, hello. I was in the middle of the class and the projector was okay at the beginning, and then all of a sudden it just disappeared. Yeah, I'm in library 317. So the projection just gone. Just didn't touch anything, you know. The people still connected. And the projector seems to be still on. Oh, okay, it came back now. Yeah, it came back now. Okay. Yeah. Okay. Cool. Okay, I'll let you know if there's anything wrong again. Okay. Yeah, thanks. Okay. Okay, sorry for the interruption. So let's continue at here. Alright, so coming back to this integral here, okay, so what I want you to really establish concept with this. Okay. So what really happens here is when you're doing integral, when you go from a to b, it's like basically so basically you can consider the integration process is like a recreating a certain object process. So let's say, for example, if you're going to the 3D printing shop to be asked to, can you print this guy here? Okay, yeah. So what do? You basically, okay, so I'm going to reprint this. So then what you do is you can see, okay, I'm going to print a line at here, right? Okay, and then you start to add basically lines at here. So you're essentially sweeping through this A to B, and as you're sweeping through the A to B, imagine if like you're putting lines, right, going from this one direction to the other direction. Okay. And the way that you're sweeping through it is the way or the process that you're recreating this basically a thin plate at here. That makes sense, right? Now, also you also have to be also bear in mind here is you're not doing any redundant work, right? So you know basically you go from A to B. You're not go from A to C and then go back a little bit and then go to B again, right? No redundancy. So all the way sweeping through A to B to recreate this thin object here. Okay, so that's basically what integration here, right? From A to B, no redundancy. So I'm going to use the similar concept here when we talk about a double integral here. Okay. Yeah. So just bear in mind about this concept, the sweeping concept, right? This sweeping concept here. Okay, so let's talk about double integral. So double integral is a mathematical concept that can be used in many applications. However, I thought it probably would be helpful to illustrate this double integral concept using a specific example right here. Okay, so here is basically the example I wanted to illustrate here. So let's say I have a function given. I have function basically z equal to f of xy given. Okay, so given right now you have this guy, and this is a surface. We all learned before. It's any kind of surface is possible. Now, this surface is not an arbitrary surface. Arbitrary basically means you can vary this xy value arbitrarily to any big numbers you want. So in this particular case, what we ask here is we restrict the xy value, okay, to a certain region. So this basically here, given this function and also given a region and here, let's call it region R. Okay, so you have a region R. The region R I draw arbitrarily. It could be a rectangular region, could be a circular region, right? It could be any type of region in here. So essentially, we limit the x and y, okay, to this region R at here, right? So this is the region R. So now the question here is, what we're going to follow here is, can you find the volume, right? The volume below z equal to fxy, okay, and above this region R. Okay, so this is the formulation of the problem here. So you have like let's say any type of object sitting, any type of surface sitting on the top of the region R. Then what's the volume below that surface and on the top of the region R here? So you can certainly imagine that if you go from any point in region R, you go up, right? You go up here, okay. So any time when you pick the boundary and you go up, and somehow you basically will trace out a certain type of curve on the top of this region R, right? On the surface S, surface at here. So your volume, what we're looking for is basically it's the volume, right, below this part and above the region R. So that's the formulation problem here. Okay, yeah. Okay, so let's see how can we solve this kind of question. Okay, it's very much like solving that question, previous question, finding the area below the curve. So what we can do is, so we can do this. So first, let's find anywhere inside this region R a point. So let's say we call this point, let's say x of k, y of k. Okay, so here's a point x of k, y of k, and then we construct a very small rectangle. Okay, yeah, rectangular area around this x of k, y of k. And what we can do is we can limit the rectangular area, saying, okay, so for the x side here is a delta x of k, then for the y side here this is delta yk. So there's this little bit change in the x side, x direction, a little bit change in the y direction, in order to create that small rectangular area. Okay, yeah. So now we extend this rectangle. Okay, extend this rectangle all the way up to the top surface. Okay, which is hovering above this region R. Right. So you extend all the way up. Okay. So once it's there, it may not be a rectangle type of things anymore, but it's more or less like that. Okay, so you extend all the way up to the top surface there. So there we go. So basically, around this location, what you just created, it's like what you just created is you created what? A rectangular box, right? So you just created a rectangular box. Then the same idea, if you pick another location, then you can create another rectangular box, right? So you create as many rectangular boxes as possible. Really depends on how you section this X and Y, right? Depends on the size of the region R there. Okay. Then you add all the rectangular box volume up, then you get the total volume, right, underneath surface above the region R. So that's the point in here. So then let's just look at this one single rectangular box here, right? If I look at this one single rectangular box, so the volume what's going on here? Oops. So the volume of one rectangular box is equal to the base area times the height. And base area, as you can see, is basically delta xk times delta yk. Maybe write one more step here. So let's say base area is delta ak. The height, what's the height? Because this rectangular box is constructed around the location xk, yk. If I go up to the surface, then at this surface location, the height is f of xk, yk here. So the height basically is f of xk, yk. It's a z value, right? The z value. The z value times the base area give you this one single rectangular box area. And then that equal to basically delta xk, delta yk. Okay? So that's the single basically volume. Okay? The single volume of this rectangular box. Then apparently you're looking for is the total volume here. So the total volume will be approximately, when you add all of them up, so you add them up, so let's say there are n number of them. Okay. If there are n number of them and then you add them up, that's a summation sign. Okay. Okay. Now, and of course, this is approximated the volume below the surface above the region R. And if you don't want it to approximate, then we basically will let this number of rectangular boxes go to infinite. If it goes to infinite, then you get precisely the volume here. If I let this go infinite, then the delta xk will go to 0, right? But it's not really 0, it's going to go to basically dx. And delta yk will go to basically a dy, infinitesimal. Okay? Infinitesimal. So then I have a formula now for basically the volume that we're looking for at here. Okay, so the volume will become an equal sign, not approximate anymore, and then this summation sign will become basically a double integral. Okay? So the f will become just f of x here. This delta will become a straight d. Okay? And what are we integrating? We're integrating over this region R. So with the subscript R at here. Okay. Now this is basically where you see the double integral coming into this picture here. Okay, yeah. Now that's double integral. So the writing of a double integral, okay, this is also I often emphasize, write it properly. You write two integral signs with a subscript r. For now, it's basically indicating this is how where you're integrating with. You're integrating over this is region R for the x, y. That will define the range basically for the x and y here. Okay. Yeah. So for this formula, for this derivation here, I use an example saying, okay, so this is the volume, right, below this surface, above the region R. So that's what we derive based on that assumption. But for other purpose, okay, if for general purpose, it doesn't necessarily this formula here will always mean it's a volume concept. It can be actually means many other things. As we later will learn, we'll learn application of the double integral. So this function here could be the density of a certain same plate. Okay, so that's the density of concept. And it could be a temperature concept. So it could mean many other things. You know, basically, then that double integral will not just give you volume; it will give you a completely different physical meaning, right? Okay. So just bearing in mind here, but this is a general formula, but the derivation here use the volume to illustrate how this derived here. Okay. Yeah. Now, if you look at this formula here, right? Next question is computation of this. Okay, computation. Computation basically means we can, of course, we can do the way that approximation, like as shown at here. You can always create a rectangular box and add them up, and then use the limitations, and you get the total volume. That's fine, right? But that's not going to be a very efficient way of computing it, right? So we really want is a more general, more efficient way of computing it. Okay. So let's look at basically a different mechanism to compute this double integral here. Okay. Yeah. So the computation here, what I wanted to do is I want to use a simple concept. Okay. Basically a loaf of bread. Okay, for illustration here. Okay. So we all eat the bread. But we never considered to calculate the volume of the bread, isn't it, right? So let's say we wanted to calculate the volume of the bread at here. Okay, yeah. If you never learned double integral, so I'm sure the guy who cooked the bread probably answered better. Is let's just slice it, and then you get the volume of each slice, and then you add them up, right? And you get the total volume. Okay, yeah. So that's a very efficient way, isn't it, right? This is actually the way to do the double integral here. Okay. So what we can do is you can always construct basically a coordinate system, okay, and you put the loaf of bread into the coordinate system, okay, and then you can always define now what type of basically region. So if you look at the loaf of bread here, what's the region? So basically the region here is the bottom here, right? That's the region. So this one here is your region R. Okay. At the same time, the bread has a certain type of surface. Okay. Yeah. Very fluffy here. So this is basically your z equal to f of x, y. That makes sense? Yeah. So now the formulation is basically falls into the similar basically formulation. What's the volume below that surface and above that region R? Okay. Yeah. So that's the idea here. So in order to calculate this this volume here, so I'll use a slightly different graphic here to illustrate this. Okay. So let's say this is my bread here. So what we're going to do is we're going to create a slice first, okay, and then get the volume of the slice, and then add all the volume. Add all the slices up to get the total volume here. Okay. Yeah. So the idea is basically is to get the volume of the slice of bread first. Okay. The volume slice bread. So if you look at the volume of the sliced bread, so this is basically one cut, right? You cut it, okay, right there. Okay, that's not a slice yet, isn't it? That's just a cut. Let's just give you a cross section. Okay, yeah. And a slice basically means you create a very small, basically delta x at here. So that will be basically a slice, isn't it? Right? That basically give a slice. So then you can easily see, okay, the volume of the slice is equal to what? The area of the slice. Okay, the area of the slice, and then time, okay, the thickness. So it's time the thickness of slice. So that'll give you this the volume in the one single slice of the bread. So the next step, then what you do is you will try to get the volume, okay, volume of the bread. Okay, in this case, any type of solid basically. Okay, so that equal to what? Equal to the volume of one slice time, okay, the total number of slice. So this is naturally the way to get an approximated volume here. Okay, yeah. But let's turn these two steps into a more formal mathematical formulation set here. Okay, yeah. Okay, so the red one represent this cross area of the slice at here. Okay, so the red color. Okay. So the slice at here, you cut it basically arbitrarily anywhere, okay, along this x-axis. Just arbitrarily you cut it anywhere. So there's always basically a minimum and a maximum value here, right? There's always a minimum maximum value. So when you have a region R, then you can always find an edge representing this minimum and a maximum x value set here. Does that make sense? Yeah. So if I look at the red color slice it here, so basically you look into this direction. Okay, look in this direction. So that's essentially z, y. Essentially it's z and the y coordinates, right? If you look into that, then you probably what you see here is, okay, so this is how it looks like for that one particular slice. Okay, so I'll use maybe red color. Okay. Good. And the one side here, this is y mean, and this side here is y max. Good. So you see that y mean is this side of curve, y max is this side of curve. So now you can imagine the bread bottom region, right? This side and this side may not be a constant, right? You know, basically maybe a curvature type of a region, bottom region here. Then it really depends on where you do the cut. If you cut it here, if you cut it here, if you cut it here, then that y mean, y max will actually be different, isn't it? Right? Yeah. But either doesn't matter where you cut. This y mean, this y max, they can be represented using maybe a mathematical expression for this curve on this side or this curve on this side here. Does that make sense? Right? So I can say maybe this is f2x and maybe this is f1x. So they're just two different functions, okay? Two different curves or different functions. So that y mean, y max depends on really where you cut it. It gives you a certain value, okay? Yeah. Where is it from? You're from f1x and f2x. Okay. So now you go back to number one step. You're looking for the area of the slice. So basically, we're looking for what? The area of this slice here. So step one. Okay. The step one here. The area of the slice equal to, right? What's the area of slice? It's the area of this slice at here. Okay. And the area of slice equal to integration below this curve here, isn't it? Below this curve. Okay? Yeah. Now what is this curve here? What's this curve? The top curve. It's what? Z equal to y f of xy, right? Yeah. So this part of the curve, maybe it looks like curve, but it's actually from the top surface, isn't it, right? Yeah. So that's basically, it's the z equal to f of x y here. Okay? Yeah. So your integration is basically, you're integrating this function with respect to what? With respect to this direction here. This is the y, right? You're integrating basically with respect to the y at here. And you're sweeping from this y mean to the y max. So your integration is from y mean to the y max. Okay? Yeah. So now you tell me, when you do this integral, it probably looks strange because I'm integrating with respect to y, but then I also have the x over there. What do you do with the x? You keep it as constant, exactly, right? Because you see the way that you're cutting here, you cut it this way here. Does that x change regarding that slice? No, right? So here you're going to treat the x as if it's constant. Okay. So now you will get the area of one slice, right? The area of this one slice right here. Okay. So you get the area of the one slice, but we really wanted the volume of this one slice. So we use the area of the slice times the thickness of this one slice. So I said, let's just give a little bit variations, okay, from the red one to the blue one. So you look at the variation. It's from red to the blue. Along which direction? Along the which axis direction? X-axis direction. So basically you are increasing the original x by a little bit. So let's say we increase that by a very little bit to delta x, right? Yeah. So if I use maybe a really small, then I will call it dx, right? So that's a very small increase for that slice to give me one piece of bread here. Okay. So basically your volume of one slice is equal to this integral here. This integral, this is the area, then time the thickness, so time the dx. Okay? Yeah. So now you get the volume of one slice, right? Get the volume of one slice. And the next step is you add all the volume of the slices up. Adding them up is basically a concept of doing what? Integration, right? Yeah, integration here. So the next step, total volume, is basically you're adding this up. What you're doing is, so I'm gonna write writing this one down in here again first. Okay. Adding up basically means you're integrating. You integrate throughout this x-axis. So now you have x mean to x max. So that's how you're summing all the pieces, volume of the pieces up to get the total volume in here. Okay? Yeah. So now you see, now this way here, you have a calculation of the double integral now. There are two steps integration. One is do this, and second is do this. So inside out. Okay, so that's the double integral here. And then you probably will see, okay, so that actually doesn't look very strange now, because we all learned single variable integration. So it's really just about single variable integration now, right? Because inside you treat x as a constant. You're basically like doing single variable integration. And once you finish this, then you do another single variable integration. So, but you just have to keep in mind which one is being treated as a constant. Okay? Yeah. So that's basically what double integral is. Okay? Yeah. Double integral also have a so-called a sequence of order added here. So now you see the order of sequence that we're doing right now is what? We do the integration with respect to y first, and then we do the integration with the nexus with respect to the x, right? Okay, because why? Because the way I created a slice in this case here is I created by cutting the slice like this, or basically you go in the y-axis direction. Okay, that's how you do the cutting first. Of course, if you wanted to do a completely different direction of a cut, if you wanted to do this way here, cut it, which is absolutely fine too, right? You can still create the slices, you can still find the total volume by adding all the slices up, okay? Yeah, but that will change the order of the integration, okay? That will change the order of integration here. So basically for now, you need to bear in mind there are always two different orders. One is dy dx, and the other will be the dx dy. Okay, so order of the integration, that actually sometimes actually matters. It could save you computation for one order of integration than the other, but the results should be the same. Okay, so then in this case, if I change the order of integration, so the writing will be just slightly different. Okay. Yes. Yes. You could actually, you could, but that would completely change the aspect for the coordinate system, because the way the coordinate system right now, you see here, is z equal to f of x, y, right? So you express the z using x, y coordinates. So if you express this y equal to f of x, z, for example, so you should reorient the coordinate system. Make sure the bottom is what? Bottom is x, z, and then the vertical is the y. And then you start to do the cutting as you wish, right? Yeah. As a matter of fact, sometimes you probably will do that. You do that way than this way here. Okay. Yeah. Really depends on. Sometimes really depends on how that object is oriented in the 3D space. Yeah. Very good point. Yeah. Okay. So let's give a very simple example first. And basically, in this example here, we're talking about is a very simple region R. Okay. So in this example here, it's a simple region R. What's a simple region R? Basically, when it's a simple region R, we're talking about a region R that is a rectangular type. Okay. It's a rectangular type here. When you have a rectangular region R, so okay, so for example, if I draw a rectangle in the xy coordinate system, okay, then you can always do this. Okay, and this is your x min, this is your x max, this is your y min, this is your y max, and that could be basically means constant, right? A to b and then c to d. Okay, so that's the nature of rectangular areas. Your x is always between a and then b, and y is always between c and then d. Okay. And this is the simplest type of region R you could have. Okay, and for this type of region R, then the double integral is actually quite simple to solve. Okay, quite simple to solve. So let's use an example to illustrate this idea here. Okay. Okay, so here is a, let's say I have a function f of x, y here, which is z equal to 4 minus x minus y. Okay, so this is your region R, the typical simple region R. Now, I will define this region R now. So region R is given by x greater than 0, less than 2, y is greater than 0, less than 1. Okay. So let's see, the question asked is, can you find the volume, right, below z equal to 4 minus x minus y and above region R? Yeah. That's a statement of the question. So let's maybe let's sketch this kind of question here. Okay, so let's sketch that. First of all, you can sketch this region R first. If you look at this region, x between 0 to 2, y between 0 and 1, so 0 to 2. So let's see, 0 to 2, 0 to 1. So your region R is really just this guy here, right? Okay, that's your region R. And then you can sketch this top surface. So here you have a z equal to 4 minus x minus y. Can you tell me what type of surface top surface is? So it's a what type of surface? It's a plane, right? Yeah. Now, if you don't have a computer, it's probably kind of hard to really properly sketch this one here. So that's fine. So always illustration is okay, right? Will help you. But basically, there are some tricks that you can have to sketch a plane. In that trick, essentially, try to sketch out the intersection between the plane and the three actually xy plane, xz plane, and yz plane. If you sketch out the intersection lines, then you can roughly sketch out this one here. Okay, so if you do that, and you'll get something look like this. Okay? Okay, so that's the top surface. Z equal to 4 minus x. Okay, 4 minus x minus y. Good. Okay, so we're looking for the volume of this irregular box over here. Okay, so here's the idea of doing this. Basically, use the idea that we're like slicing a loaf of bread, right? The first step. So first step is always actually to choose the order of a sequence. So order sequence, whether you want it to dy dx or dx dy, basically. Okay. Let's say I'm going to use dy dx in this example here. So then what we do is we can pick any point, okay, anywhere between 0 and 2. We do a slice or we do a cutting. Okay. So basically, I'll summarize after this example here. Okay. So we can slice up, okay, anywhere in between to create a cross section here. And then you will basically sweep this slice, right? You will sweep this slice here all the way from one end to the other end. So this is essentially like creating this object here, right? This is like creating this object. Same idea as this, like a 3D printing. When you do a 3D printing, so you always just print one layer first, and then all the way up, right, to the end of the object, isn't it, right? So it's like you create a slice here, but in this case, I create a slice arbitrarily. Then you can think of this slice moving from one end to the other end to create this whole object here. Okay, yeah. So when you do this slice here, if you look at the slice here, this is why the simple region here, really why it means a simple. So the area of the slice at this end here, the x is always what? 0, right? That's right. X is not 0 here. X is you go from this end to this end. So the y is always what? 0 to 1. Okay? It's always 0 to 1. So from one end to the other end. And then when you go from this end to this end, your x goes from 0 to 2, right? 0 to 2. So your integration basically telling us here is your x mean is always 0, your x max is always 2, and your y mean is always 0, and your y max is always 1. Okay? Then the volume or the double integral, okay, Okay, so this is a double integral here. Okay. So I can lay down this structure of the double integral now. The inside here is f of x y, which is 4 minus x minus y. I'm doing dy first and dx. Okay, so that's the idea. Okay, so you look at the limits for the y. The limit of y is always go from 0 to 1. So it really doesn't matter where you do the slice. The y always goes from 0 to 1. And then the x, you're sweeping from one end to the other end, and it goes from what? 0 to 2. Okay, root 2. Okay. Now that's the setup for the double integral here. Right? That's the because it's so simple, the region. So all you see the limits here, they're all constant, right? The limits for the integrals are all constant. For irregular region R, instead of rectangle, as we're going to show you next, the limits here, okay, for the outside limits, it will be a constant. For the inside limits, sometimes it carries as a function. Okay, it depends on the sequence. Maybe here's x, maybe here's y, and it depends on the sequence. Okay, yeah. So I think everybody should be able to evaluate this integral very easily, because for the inside integral, you're integrating with respect to y, so you treat the x as if it's a constant. Huh? Yeah, so always bear in mind now, so treat the x as constant. So the inside integral here, so this one give you 4y, this one give you what? xy, and this one give you half y, 1/2 y squared. Okay. And then the limit goes from 0 to 1. Okay. That's the result of the internal integral. And overallly, you get 0 to 2. Substitute the limits into it. You're going to 4 minus x minus 1/2. Okay. So that's this one here. And the last one is there's only one single variable left now. And that's quite simple. So in the end, you're gonna get a 5 here. Okay, 5. Now always remember, okay, when you end up with just one integral now, there should be only one variable left. You shouldn't still have another variable y in here, because if you still see a y in your writing, then probably there's somewhere is wrong. Okay, yeah. So you can practice here. If I change the order of integration, instead of dx, instead of dy dx, let's see if I do dx dy first. So easily you can change the limits. The x goes from 0 to 2, and y go from 0 to 1. Okay, so you should get the same, basically, the same results, which is also should be 5. Okay. Is that good? Yeah. So that's basically the essence of double integrals. It's very, actually not very strange now, because what it involves is actually a single variable integral now. Okay. Yeah. So, but I do want to summarize here is, not rectangular, but really a non-rectangular. Okay. So what if we deal? That's typically what we deal. Okay. If we have a non-rectangular area, how do we basically do the double integral here? Okay. I will illustrate this using a specific type of region R. Okay, to illustrate this idea. Okay. Yeah. Okay, so number one step, what you typically should do is sketch this region R. Now this a little bit challenge to sometimes to some people. You know, sometimes you have a hard time to visualize what really region R means, really R look like. But it's a very essential skill to have. Okay. Sketch the region R, and you should also label the boundaries. For example, okay? For example, we said, okay, region R, okay, is bounded by x squared plus y squared equal to 1 and x plus y equal to 1. Okay, so that's one example. Bounded by two curves, okay, region R. So sketch. Let's take a look at what does it look like. First, you sketch the circle. So you can sketch the circle, okay, like that, with a radius 1. And second of all, you sketch this one, x plus y equal to 1, which is a straight line, right? There's a straight line here. So the straight line, to sketch that, and it actually happen to be from here to here, right? So this is your x plus y equal to 1. Okay. Good. Okay, so in this case here, you can actually argue it's not quite that clear. When you see a boundary by these two curves, so it could be what? It could be this, or it could be this, isn't it? Right? Yeah. Yeah. So let's say in this case, if I give you a little more specific regions, let's say x is greater than 0. Okay. Yes, x is always greater than 0. If x is always greater than 0, then this we're really talking about is this part here. Okay. So let's say in this case, I'm going to really to look at this. This is the region R here. Okay, so cool. Yeah, so that would be a rough sketch for this region R, right? So you label the boundaries. Label the boundaries. This is the circle on the top. Here's the straight line at the bottom. Okay, so that's your first step you should typically do. If the question didn't sketch for you, you should do this. Okay, and then so we're integrating through this region R. Basically, we're doing this. We're gonna do this at here. Okay, I don't know what type of a function we're going to integrate, but I do know I'm going to integrate through this region R here. So you can imagine if I really wanted to draw this here, region R is at the bottom here. This is your region R, x, y. And then the f of x, y is somewhere on the top here. Okay, somewhere on the top. And you can rethink, this is just trying to find a volume between below that surface and above this region R, right? Okay, that's a double integral. Okay, yeah. So what do we do here, right? What we do here is, if you look at the idea of the double integral here, it's basically trying to sweep through this region R, but without redundancy. Okay, and there are different ways to sweep. Basically, whether you do sweep the x-axis first or the y-axis first. That's what we call the order of integration here, right? Yeah. So the second step here is to decide on the order. Let's say, for example, dy dx or dx dy, right? So that's the order, basically what it means here. If you write it dy dx, basically means you're trying to integrate the y first. If you write a dx dy, then you're integrating dx dy first. So I'm going to use a dy dx as illustration. So we're going to integrate as order dy dx. Then I will redraw this. I'll redraw the region R at here. Okay, it's a little bit bigger here. So this is your region R here, and this is 1, this is 1. X squared plus y squared equal to 1. S plus y equal to 1. Okay. So if I'm going to go dy dx first, so the next step, this is what you do, and the next step here is to find the y limit. Sorry, because you're doing dy first, so the next step is to find the y integral limits. So how do we find the y integral limits? So this is what you do. You will, this is region R, you will draw an arrow line, okay, in the positive y-axis direction across this region R. You don't draw it here or here, because that doesn't across region R. So you draw it, okay, somewhere here in the positive y-axis. Basically this should be parallel, huh? These two, across this region R. Okay, that's what you do here. So draw an arrow line, draw an arrow across region R, okay, in the positive y-axis direction. Okay, that's the sub-steps basically to find the y limits. When you finish this drawing, so you can imagine basically, okay, I have a little person here start to walk along these arrow lines. It'll go, and then up to this, it'll come in contact with this region R, right? This is what I call the first contact. So first contact give me the y mean. Okay. And keeps going up, it'll bump into the second boundary of this region R. So that'll give me the second contact. And that will give me the y max. Yes? No, you can't. Because this is basically the arbitrary sweep at this stage, the first sweep, right? It's not a specific sweep, okay? Now, so when I draw this, you can imagine basically what happens is, if I look in the 3D, you're doing this, right? Basically you're doing the cutting over here, and then somehow you create a slice. That makes sense? Right. So what I draw here, of course, I just only focused on the region R, right? Yeah. So technically speaking, what does this step do? This step will create basically this black segment of line. Okay, that's the first step. It created that black segment of a line here. That makes sense, right? Yeah. So in this particular example, first contact is the bottom straight line. Second contact is the top circle boundary. So can you tell me what is the y mean? What is y max? What's y mean? X plus 1. It's not a number. It's defined by this curve, right? No, x plus 1. Yeah, 1 minus x. Yeah, almost got it there. So, second contact is the circle. Circle is x squared plus y squared to 1. So the y should equal to. That's right. But you do have a negative. But then in this case, the first coordinate, so you get rid of the negative, right? Okay. So that's your y mean. This is your y max here. Okay. Yeah. So in terms of integration, we're looking at is the integration now. Next is for this area here. Basically, that's your y mean, y max, right? To do the integration. Okay. Yeah. Very good. And once you finish this step here, okay, the next step is to find the x limit. Okay, the x limits. So your y limits is found, and then you try to find the x limits. First step, what do we create? We basically create a black segment of a line here, right? Second step here, find the limits, basically to sweep. Okay, sweep this arrow line, okay, across the region R. Okay. So sweeping basically means you move this guy to one edge, and then start to go to the end of the edge here, right? To the end of the other edge of the region R. So basically, you look at this one here. What are the two edges? one edge is over here, and the other edge is over here, isn't it, right? That's the two boundaries, two edges bonding this region R. And this edge corresponding to the x mean, and this edge corresponding to the x max. So your sweeping will result in basically two edges corresponding to x mean, x max. Okay? Yeah. Okay, so the two edges will give x mean and x max. In this particular case, x mean equal to 0 and x max equal to 1. Okay? Yeah. So now you can come back to this region here. If the first step create a small segment of a line here, then the second step is like you're sweeping this line, small segment, across basically this region here. So it's like a dragging. It's like a dragging some sort of a curtain, right? All the way from one end to the other end. As you're doing this, you're recreating, or basically you're finishing the sweeping of this region R. Okay? Yeah. No redundancy. From one end to the other end, you recreated this region R here. Okay. So finally, you can put down this double integral after you find the limit set here. So the first step, you can always write this down, right? You can always write this down first, because that's the order we chose, dy and dx. So dy, the limits goes from 1 minus x to root 1 minus x squared, and dx goes from 0 to 1. Okay. Now this is the setup for double integral, and then the rest of the job is basically to integrate inside out. As doing the first integral, you will treat the x as if it's a constant. Okay? Yeah, treat it as a constant. Finish this, you get an expression for x only, and then you integrate respect to the x next. Okay? So this is results for dy dx, right? Yes.
Will the outer limit always be numerical, like from 0 to 1, or can it be a function as well?
No, the outer limit's gonna have to be numerical. Yeah, you cannot have a y at here or something, right? Because otherwise, if you have a y, for example, then the end result is still a function of y, right? And that doesn't make sense. Your volume will be well, unless sometimes you purposely do it, okay, up to somewhere arbitrary location. But if you're specifically asking within the region and above the region, below certain surface, and then it's going to be a numerical value right here. Yeah. There.
If we do the unbounded integral, would we include the constant in after the first inner integral, or would we only include the constant at the very end?
Unbounded meaning like there's infinite things like that. You probably will put it, depends. You probably put it outside here. Yeah. So for the internal one, right? The internal one is arbitrary cut, and that you typically should have a limit for that first cut. Yeah. Yeah, the infinite one, I don't think you're gonna ever see that though. Yeah. Okay. Is that good? Good. Yeah. Okay. So I want you to practice this. So let me change the order dx dy. What will be the limits for the x, and what will be the limits for the y? Okay, just give you 20 seconds here. Let's see if you can put these limits down. Okay, so if you do this, then your cutting will be this direction, right? Cutting will be this direction. Or the first step, the arrow lines will draw to that direction. Okay. So what do you get for the x limit? Lower limit is y minus y. Y minus y squared. Good. Same thing, right? Yeah. Good. So as long as you keep a clear mind of the sequence and the cutting here, and you label the boundary clearly, okay, correctly, then you shouldn't have a problem with the limits. Okay. This is very important because if your limits are wrong, then the rest of the computation will all be wrong, right? So the first step of setting up this double integral is a very critical part of this exercise here. Okay. Okay. So let's look at a slightly different. Let's look at a simple example, an exercise here, and then. Alright, so let's see if this is region R. Okay, this is region R. So I sketch for you. Maybe if I give you a description, then we'll say region R is bounded by y equal to x, x equal to 1, and x-axis. So that's basically the description for region R, and that will be the sketch for region R, right? Okay. We wanted to integrate a function sitting on top of this region R, which is a plane, so 3 minus x minus y. So let's say if I decided to do this double integral, and by following the procedures illustrated on the just on the top there. So then let's see what will be the integration result. First step, you sketch and you label, which is what I just did. Okay. And second step, you decide on the order of the integration, either dy dx or dx dy. Okay. In this case, actually doesn't matter. In some cases, really matters. Okay. Yeah. We decided to say dy dx here. Okay. Yeah. So basically, we're gonna integrate this function by dy first and dx next. Okay. So that's the general setup, but we need to figure out the limits, right? Okay. So if we do this, so we're gonna basically, according to the steps, we will draw an arrow line, okay, in the direction of a positive y-axis, and then you imagine moving along this arrow line. The first contact between this arrow line and the region R will give you y mean. So in this case here, y mean is always what? 0. And then you go up until you have the second contact, which is the exit point, right? So one is entry point, the other is exit point. That'll give you the y max. And y max is happen to be on this straight line here, so which is x. Then you sweep this line across this region R, right, from one end to the other end, to basically recreate, to sweep through this region R. And that go from one end, which is here, to this end here, so that go from 0 to 1. Okay. Yeah. It's very simple. And then the rest of the work basically is integral now. So first integrating the inside by treating the y, the x as a constant. So that gives me 3y minus 1 minus xy minus 1/2 y squared. The y goes from 0 to x. This is actually a common mistake. You should be careful here. When you do this step here, sometimes if your mind is bothering you, is not troubling you, then you perceive, okay, so what am I integrating again? Or you say the x goes from 0 to x. This is actually for limits for the y, right? So only the y goes from 0 to x here. So that's something you got to be careful here. So that gives you basically, will give you 3x minus 3x squared over 2 dx. Okay. So finally, you can easily do that integral. You get number 1. Good. Okay. So I think if you follow the procedures as I laid down there, then you should be fine. You shouldn't have any problem or challenge in terms of the double integral here. Okay. Any questions so far? Okay. Okay. Yeah. So I'll give you a slightly different example in this here. It's not about a computation. It's more just from a different perspective of double integral here. Okay. Yeah. So I'm going to give you a double integral. So 0 to 2. So here's the double integral. The question here is, can you sketch this region R? So it's a reverse engineering. You were given a double integral with limits, and being asked to sketch the region R where the integral limits are from. Okay? Yeah. So that's like a reverse engineering. So in this case, you basically you're going to have sort of establish a correspondence to the process how you find the limits there, right? Yeah. So how you find the limits here is first decide the order. In this case, what's the order here? It's a dy dx. Okay. So whenever you have a dy, basically means the first step is what are you gonna do? You draw the arrow line in the positive y-axis direction, right? That's the first step. So when you draw the positive arrow line in the positive y-axis direction, first contact give me what? The y mean. Second contact, or the exit point, give the y max. So basically what it's saying is, if you draw basically arrow lines in the positive y-axis here, what was the first contact? Y equal to x squared. So you're going to draw a y equal to x squared here, right? That's your first contact. And then the second contact, which is the exit point, is y equal to 2x. So you can draw the y equal to 2x. Okay. Yeah. That's how you find the two limits at here, right? And then you sweep this arrow line from one end to the other end to find x min, x max. So in this case, you find it 0 to 2. So apparently, the two curves intersect at this origin. So that will be one end at here, right? That will be one end. And the other end, if you solve this one here, that end actually happened to be 2 at here. Okay. So basically, your region R is this little piece at here. Okay. Yeah. So if I have a subsequent question in here, if I ask you to re-evaluate this integral, but evaluate it in a different order, dx dy for order here, and what will be the integration limits? Okay, give it a try. So dxey basically means you will draw the arrow lines in this direction now. If you draw it in this direction, this is your first contact, x min, the second contact, x max. So what's the x min here? Y over 2. What's x max? Square root of y. And then the limit goes from 0 to 2. 4, that's right. This is 4 here. Okay, good. All good? Okay, so last example, which you don't have to write the last example is just to illustrate why I'm going to introduce a new topic in the next lecture. Okay? Okay, so here's the double integral problem here. So we're integrating this function, okay, over this region R. If I do a sketch for the region R here, it basically is the quarter circle in the first quadrant here. Okay, yeah. Okay, so I'm going to carry out this double integral the same way as I did for the other examples here. So this is what I'm going to do. I'm going to choose order which is dy dx at here. Okay? So then I'm going to choose this order here. Now if I choose this order here, what will be the limits? Okay? You draw an arrow line in the y-axis direction. Y means 0. Y max is over here, which is root 2 y minus x. Sweep this 0 to 1. Okay, yeah. Is that good? That's very simple. Okay, so now you're happy that you set it up. Let's do the calculation, right? And then you're actually not so happy anymore. Okay, so if I do this one here, this is y squared, so 1/3 y cubed, and that goes from 0 to 1 minus x squared dx. Okay, so the 1/3 can be moved out here, so 0 to 1 here, so you end up with 1 minus x squared cubed dx. Okay, so right here you end up with this integral here. Okay, now this I think probably 99.9% of you will, actually I wouldn't be able to do it if I don't have a formula. Okay, so this is not a pretty integral to do in the exam here. Okay, you can try substitution. You can let x equal to sine u. Okay, and basically you do need a formula, okay, for this kind of question. Okay, and I can show you the formula, but that's the point here is it's almost too challenging to do this kind of integration in exam. So the question here is, do we have another approach or different venue to solve this double integral? And pardon me, you will have a similar problem. Yeah. So the answer is we're going to use a different coordinate system. Instead of x, y Cartesian coordinate, we're going to use polar coordinates. Okay? Yeah. I'll see you next week. Yeah.
Can I just ask you